Okay, so I only had a couple of, couple of questions on the discussion for the test for Friday. So it was fluorescence. Where was fluorescence used in the discovery of X-ray, or where was it observed? And that would be in the glow of the plates. Whenever Rinkin covered up the X-ray tube, or the Crookes tube, and still energized it, you can see the plate across the room glow, and it demonstrated fluorescence. All right, so fluorescence is just glow in response to the stimulus. Fluorescence developed into what we use to cut radiation dose back in the intensifying screens. They also demonstrate fluorescence, right? So we'll put the X-ray film inside of a cassette. The cassette contains intensifying screens. Y'all remember the video? I'll post those. Yeah, okay. So you make the exposure on the screens glow, and the glow is what actually, yeah,
sorry.
there you go. Is what actually, yeah, if I gotta do it, you gotta do it.
Sorry.
Is what actually exposes the film, right? So, that's fluorescence. What it developed into was fluorescent screens used to make diagnoses in, before Edison developed a fluoroscope. The only thing we could really diagnose was gross anatomy. And with fluorescence and using fluorescence in a fluoroscope, we could diagnose at least a little bit of physiology. You know, you swallow and you can actually see it go from the mouth to the stomach. That wasn't in discovery, that was in development. But I wanted to touch on that as well. So discovery is really just the glow of the plates across the room whenever he made the exposure, whenever he energized the X-ray tube. You can see the plates across the screen glow. And that's really what enabled him, and that was the discovery, right? Without those fluorescing plates, people would have just gotten exposed to the radiation, gotten sick and died, and they would have had no idea what it was. So that's where it was used in discovery. Primary barriers was the second one. Difference between primary and secondary barrier. A primary barrier is anything that you're likely to point the X-ray tube at. So the floor would be a primary barrier. And what the primary barriers need to have is enough of a substance that would absorb X-rays to prevent X-rays from penetrating through to the next adjacent structure or room or whatever. So it could be concrete, it could be lead, it could be almost anything that absorbs X-rays as long as there's enough of it. Like a primary barrier, I think if it's concrete, it has to be like a foot thick. If it's lead, it doesn't have to be as thick, but it still has to block the X-ray. So that's a primary barrier. As opposed to a secondary barrier would be anything inside of the X-ray room that is likely to catch scatter radiation. So you're never going to point the X-ray tube directly at the window where you're standing behind the control panel. So likely, if in the construction of an X-ray room, they could make that a secondary barrier. Walls, ceiling. If it's a wall that is not, the X-ray tube is never going to be pointed directly at it. That could be a secondary barrier. Ceiling certainly could be a secondary barrier. In my entire career, I've aimed the X-ray tube at the ceiling one time. And we'll talk about that next semester when we get into facial bones. So primary barriers, anything that the X-ray tube is definitely going to be pointed directly towards. Secondary barrier is still in the room, but not directly pointed towards it. So scatter radiation. And then potential. And this is where we're going to spend a little bit of time because potential is confusing. Okay? So we say KVP is potential, right? It's electric potential. It is or voltage just is electric potential. So the terminology is, a little confusing. So We say that the KVP being the electric potential is what gives us our kinetic energy. But we say that KVP is not applied, or is definitely not applied, until we want to make exposure. So what we've got, whenever we hit our prep button, is just a collection of electrons around the filament, and we call that what? Hot ions. Hot. What kind of radiation is heat? Thermal. And what are ions? Charged particles, so electrons are ions, right? So thermionic emissions is what we call that. Collection of electrons around the filament. So thermionic emissions, which is a space charge, right? So when you hit your prep button, that's what you get, right? So you're gonna have a tendency to think of that as they're being positioned here. So you've got the being potential energy being the energy of position. They're positioned in a place where they can go across and make x-rays. So logically, and I'm right there with you, you're gonna consider that kind of like your electric potential or your potential difference or your potential energy. You got the potential to make x-rays, you just don't have the ability until you apply the KVP. So the KVP then becomes the potential that sends them across the x-ray tube. So KVP equals electric potential, which equals potential difference. Potential difference. Okay? So we don't get kinetic energy across the tube, and again, you're going to be, some of you may be thinking, well, if we got a flow of electrons, the flow of electrons goes around like that. We've got kinetic energy. You're right. But the kinetic energy we're talking about is the kinetic energy that sends the electrons not around the filament, but across the x-ray tube. Okay? So that kinetic energy doesn't come into play until we apply the electric potential, which is the KVP. Okay? It's like looking at a crowd of owls. Okay, does it make sense at all? Where'd I lose you? The question was, where do we have kinetic energy and where do we have potential energy? Potential energy is your KVP. All right, KVP equals, just look at P, potential, KVP, okay, is your electric potential. Kinetic energy is the travel of electrons from the cathode to the anode. Okay? Kinetic is energy of motion. If we got them stuck right here, they're not moving across the tube. Yeah, they're moving through the circuit, but they're not moving across the tube. It's not until we hit it with the KVP, the potential difference, that we get kinetic energy and we get x-rays made. No x-rays will be made until we press the exposure button, press the prep button. This thing spins, this thing gets hot. We hit the exposure button and the electron, we apply the KVP and the electrons go across the tube and we get kinetic energy. Okay? I need a little feedback, folks. A little nod or what does that mean? Something. Should I go on or we're good here? We're good. Okay. All right. So a couple of things this morning. We're going to have a test on Friday. Test over chapter 1. And I hadn't heard back from the room scheduler, but I did some scouting this morning. And the 0 floor, not the first floor, but the 0 floor, all the way at the bottom, this morning had 3 empty rooms. Okay, so if we can all test, I didn't check south side room, I didn't check 3rd floor. So before class on Friday, I'm gonna check all those areas and see if we've got empty rooms. And if we do have empty rooms, we're gonna squat, and we're just gonna test all at the same time. If everybody's here, we're just gonna test all at the same time. If we gotta break up into 2 rooms, You know, if I can talk Trina into sitting in one room, I'll sit in the other room, and we'll just test all at the same time, okay? If south side room is open, we're going there, as long as I can get into it. If third floor is open, as long as I can get in there, we're going up there, okay?
So we need to be here 8 on Friday?
No, Trina's still gonna have class on Friday. Or did she tell you she's not?
Trina always does Zoom.
We do Zoom on
Oh,
Fridays.
oh, yeah, okay. Well, she's still gonna have class with the other half, no.
Okay.
So, just, you know, oh, wait a minute, y'all are, yeah, okay. Yeah, it's early yet, it was a long weekend. So Friday, y'all need to be here at 8, because Trina's still gonna have class, but you need to be here by 9:30. Okay, for the test. Okay. So, again, you know, just be flexible when we get here Friday. If we can get everybody into one room, we will. If we can get, you know, people into 2 different rooms, then we'll do that. Okay? All right, so what we're gonna talk about today, is we're not gonna get too deep into chapter 2. We're not gonna go past atomic structure. Well, we may not get into electron arrangement, we'll see. I was expecting Trina to run a little bit longer than what she did. So, you know, kind of ran out of prep time this morning. So what we're going to talk about is structure of matter and development of the atomic structure and how we got to where we are with what we think we understand about atomic structure. There's still to this day competing theories on atomic structure. There's string theory. If you ever want to, you know, chase a rabbit hole online, just do a search for string theory. It's really pretty complicated, but it's a kind of predominant competition for what we think we know about atoms at this point. So, atomic structure, you know, the development of the atomic structure and discussion of atomic structure, you know, the Greeks were a real philosophical group. And they were the ones who, you know, initiated the discussion on atomic structure. They didn't have electron microscopes in ancient Greece. But they philosophized that there was a fundamental portion of something that couldn't be divided out anymore, and it still would be that same something. They couldn't identify individual units, but they could look at water, and they could look at water and say, okay, that's water. And if I take a cup of water and I pour half of it over here, I've still got water. If I pour another half over there, I've still got water, just lesser quantities. But there's gonna come a point where I can take this water and I can divide it and it becomes something totally different, okay? And that's what they call an atom. So the definition of the word atom just means indivisible or uncut. It can't be divided out any smaller than what it is and still be that thing. It becomes something totally different if you cut it further down. We'll look at the elemental table here in a minute and kind of see what it was they were talking about. But they didn't know what those things were. Certainly they didn't know water was 2 parts hydrogen, 1 part oxygen. They just knew it was water, and it was unlike anything else, just like dirt was unlike anything else, a tree was unlike anything else. So they had the logic to say that everything was made of something that couldn't be divided, or could be divided a finite number of times before it became something totally different. That's what they call an atom. So if you flip over to page 28, what you'll see is kind of what they theorized the atomic structure to be. So you had 4 substances in 4 states of being. 4 substances they called 4 substances, and the states of being were the essences. So you had air, earth, water, and fire, and those are your 4 substances. And the states of being that they called essences were cold, wet, hot, and dry. So, you know, I'm not real sure how you have, you know, dry water, or cold fire, but, you know, I mean, they were onto something, and that was the atomic structure, and it couldn't be further divided down. So if you look over onto page 29, you kind of, we'll talk just briefly about this. What we've got there is the elemental table, right? The elemental table was developed by Joseph Mendeleev. Dmitri Mendeleev, and he identified individual elements and arranged them in ways that each one of the elements behaved in similar ways. Okay, so on the chart, each one of the elements in a table in a period behaved in a similar way. But what you see across the top, just the simplest explanation or simplest example, is all the way to the right hand side on the top. What do you see? What's the element there? It's helium, right? Helium has an atomic number 2. So atomic number 2 means that the nucleus of the helium has 2 protons in it, okay? Now if you look across on the left-hand side, all the way at the top, what do you see? Hydrogen. Hydrogen has how many protons in it? 1. So if you took helium, if theoretically you could take helium and you could divide it straight into half, if you could take those 2 protons, that's what the atomic number identifies as number of protons in an element, and you rip the helium atom in half, so the nucleus divides out into 1 proton on one side and 1 proton on the other side, what would you have? 2 hydrogens, okay? So again, atom just means uncut. If you divide an atom any further than 1 individual atom, then essentially what you've got is something totally different. So you can do that with all of those. So selenium, 34, if we were to divide that out, what is Cl chloride? If you cut it in half, that's what you would have, is atomic number of 2 elements with an atomic number of 17. So, that's the Greeks. Dalton came along in the early 1800s. Dalton came along and he said, okay, well, we've got more than these 4 essences and 4 substances. We got individual things, you know, we got these individual things that can combine to make greater things. So he had 2 contributions to the atomic model, and that was combination of atoms. So you've got different atoms combining together to create either more of that same substance or something totally different. Like, for example, we know that that water is H2O, right? So what you've got there is maybe a big oxygen with these hooks on it, and then you've got 2 of these little bitty atom or hydrogen atoms with eyes on them. Now, y'all grew up in a time where storm doors were pretty much the norm. I grew up when screen doors were the norm. So in screen doors, what you have, and you've probably seen these on something else, cabinets or something like that, you screw this little eye bolt into one, like if you've got a cabinet door that you want to keep shut, what you're going to have is this little eye bolt that's screwed into the door frame, and then you've got this other little bolt that's got this hook that comes over and hooks into it so that you can't open it. You've seen those, right? That's basically what he was hypothesizing, is that they join together kind of like that. In this case, what you have is a wall and a door. In this case, what you've got is oxygen and 2 hydrogen. Okay, so that was his main contribution. But he also, before Mendeleev came along, he sought to arrange the elements, individual elements, according to their atomic mass. And atomic mass is a behavior, or it is essentially the weight of an element. Okay, and we kind of walked through a little bit of an exercise last week. If you had a quantity of lead and a quantity of aluminum, they weigh totally different, right? Even though the quantity may be identical, the size may be identical, the weight is totally different. Okay, so two things that Dalton contributed. One is that you can combine atoms, and then he classified them according to their atomic mass. Mendeleev came along in the 1850s and developed the first elemental table and arranged them according to behavior. So Bouchon goes through examples of what those behaviors are. Like group 1 or period 1 is would be your alkaline metals. Group 2 would be halogens, and group 3 would be or group 8 rather, far right hand side would be the noble gases. So he arranged them according to their behavior and how they combined with other elements. Thomson, I don't know what Thomson was thinking. It's important to understand what he contributed, but how he came to it, I'm not real sure. Anybody ever seen plum pudding? Anybody ever heard of plum pudding? Yeah, me either. But I guess maybe it was Christmas time, and his Aunt Edna, you know, had a tendency to bring this thing that nobody would eat. It looked like a Jello mold, but it had some sort of pudding on the inside of it, and on the outside, what he had was plums. So this thing kind of in a pyramidal shape, and it's got these plums on the outside of it. He said, well, you know, that's kind of like an atom, in that what we have in the nucleus of the atom is the goo that makes the atom what the atom is, but we've also got these individual little things on the outside that we call electrons, okay? So his vision wasn't totally useless, it was just a little bit weird, right? So you got the nucleus, he introduced the electron arrangement, not the electron arrangement, but the organization of an atom in a well-defined nucleus with electrons on the outside of it. All right, so we flew with that for a while until Niels Bohr came along and gave us what we are going to use in this class as our model. And it, as we'll see, combines each one of these theories, okay? So now what we recognize is that just like the Thomson atom, we had a nucleus, and inside the nucleus we had the stuff that made the atom what the atom was. But we also had electrons on the outside, but the electrons on the outside weren't glued to the nucleus. They existed in shells that went around the nucleus. Okay, so these, I can't draw this three-dimensionally. So what you need to kind of get in your mind is that these things travel around, the electrons travel around the nucleus, but they travel around the nucleus in all different directions, okay? And what you may find if you continue your education and go to nuclear medicine school is they might not just go around the nucleus in 3 dimensions, but they might eventually and sometimes go through the nucleus itself. Okay, we're just gonna say they go around. They exist in shells, and the shells have prescribed number of electrons that can be in each shell, and they travel around the outside of the nucleus all the time. Okay, yeah.
Do they ever run into each other?
They don't bump, well, theoretically, yeah, they could, but, for our purposes, we're just not gonna get that deep into it. But, the thing that would keep them from bumping into each other is they're both negatively charged, so they're gonna have a tendency to push each other apart. So probably not, but, theoretically, almost anything could happen. Okay. So Niels Bohr, that's his model, and through further analysis of the atom, and bombardment of the atom and nuclear accelerators, they've identified a lot of subatomic particles, but we're only going to focus on 3. So we got everything that's inside the nucleus. I won't say the nucleus, but what's inside of the nucleus are the positive charges. Positive charges would be the protons. And then we've got neutral charges inside the nucleus as well, and we're gonna call those neutrons. And then on the outside, we've got electrons. Okay, so these two are what we're gonna call nucleons. And we're not gonna call it that very often, we just called them that probably the last time that we're gonna call them that. So we've got nucleus and we've got electrons. All right, protons and neutrons live inside the nucleus of the atom with the electrons on the outside. Protons are positively charged, electrons are negatively charged, and even though the protons are massive compared to the electrons, the charge is identical, okay? So one positive charge and one negative charge cancel each other out, right? So that it becomes, if one positive charge and one negative charge cancel each other out, the entire atom becomes
Neutral.
neutral, right? So we've got that. We've got one proton, we've got one electron, we've got one neutron. So we got a neutral atom. It's an atom of atomic number 1, and your elemental table is hydrogen, right? So we got a hydrogen atom here. So what I want you to be thinking of, for reasons that we'll talk about next week, is the neutron is not neutral for lack of charge, but it's neutral because it's got both charges inside. And since both the positive charge and negative charge cancel each other out, that means the neutron becomes not positive or negative, but neutral, right? So the neutron, I don't want you to be thinking it's just neutral in that it lacks charge, but it has both charges present, okay? All right, so if I were to take this out and draw 8 more orbits, and just put one electron in each orbit, what would this start to look like? I didn't get to 8, I ran out of room, but what would it start to look like? Something big in the center of something with a bunch of things going around it.
They would shows electron cloud.
Yes, well, it's electron cloud, but think bigger.
Oh, kind of
Solar system. It looks just like our solar system, right? So the model that we're looking at for the atomic structure, you know, this is so small that you can't really wrap your mind around it all that well. So what we're going to look at in comparison is kind of the solar system and how the solar system works and behaves. So I'm going to use the analogy of the solar system to describe a lot of different things in relationship to the atom. All right, so how do we get to this, or how do we know that this is possibly a viable example of how the atomic structure looks? If you were to take water, just say a tablespoon of water, and you were to put it under a microscope, or just even a drop of water, you were to put it under a microscope, you were to look at it under a microscope under maybe 1,000 times, that tablespoon of water would become about as big as this room, okay? So it magnifies it up quite a bit. Now, if you were to put a second magnifier on there of about 1,000 times, and you look down onto it, then your tablespoon of water becomes about the size of the distance between here, I don't know, and maybe the Cumberland Mall. Everybody familiar with where the Cumberland Mall is? So now it's a big lake, right? And then if you were to magnify it up again another 500 times, it becomes an inland sea, the size of an inland sea that spans from about here to Chicago. Huge, 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 right? But you still don't see anything except for water. But if you get down on the water level and look across it, what you see is it's not flat. And instead, it's kind of bumpy like that, okay? And not only is it bumpy, but each one of these little bitty things is in constant motion. It's bouncing all over the place. So we know 2 different things, is that the water is made up of individual little bitty pieces, and those pieces are in constant motion as if these electrons are blasting around the inside of the nucleus, okay? Now, looking back at the solar system, what do you know about the solar system? We got the sun, right? And then we've got the planets around the sun. But how far apart are the planets, and what's the closest planet to the sun?
Mercury.
Mercury, right. Mercury's close to the sun, but how close is it really?
Thousands of miles.
Yeah, it's a long, long way away, right? So what's the next planet? Venus, right. So how far away from Mercury is Venus? A long, long way. What's the third rock? Earth, yeah, kind of gave it away, right? So Earth. So what's the closest celestial body to us? The moon, right? How long does it take to get to the moon?
3 days?
Yeah, it takes like 3 days traveling at close to 20,000 miles an hour, right? So it's a long, long way away, right? So what does that tell you about the solar system?
It's big.
It's big, and it's mainly what? Is it crowded? You count on all the debris we leave up there on space missions, it gets a little more crowded, but no, it's not. Your next neighboring planet's a long, long way away, right? So if we apply that to our atomic structure, then what we see is kind of the same thing. If we had a nucleus, we had a well-defined nucleus that was maybe the size of a quarter, not like that, then how close do you think I would need to draw my first set of electrons, my first shell of electrons, my first ring of electrons, closest planet to the sun? Where do you think it'd be? Would this be far enough? Closer? Closer? What do you think?
I mean, the first planet isn't that close to the sun, and burn up.
Right. So
that's
where do you think?
in retrospect to the solar system, like
Yeah,
not
yeah.
even on that board, probably.
Okay. How close would you think? You're right. I wanna hear your closest guess.
I don't know.
Maybe Fifth Street, or what is this road out here? Magnolia? Maybe. It might be White's Administrative. Okay. So, I say all this because X-ray creation is very theoretical. And what did I say was the likelihood that we're going to create X-rays? Whenever we create X-rays, what's the main thing we create? Heat. On a magnitude of what? How much heat compared to X-rays do we create? 99% heat? 1% X-rays. Right. Now, of that 1%, most of what we're going to create, and we'll learn this throughout the semester, is worthless X-rays. Okay? Because what we're doing, what are the two ways that we create X-rays? One is breaking X-rays. We call that, German word for breaking is brims X-rays. Right. So what does what do we have to have in order to get brims X-rays? What do we have to lose?
Electrons.
We don't have to lose electrons. We have to lose the kinetic energy of electrons, right? And that's going to be dependent on how close it gets to the nucleus of the atom. So you've got a nucleus that's this small, and you've got this line of electrons that extends from floor to ceiling, and if they travel straight across, just straight across, how many of them are going to get close to the nucleus of the atom, that the gravitational pull of the atom, the nucleus of the atom, would redirect them and lose 99% of their energy? I don't know, not many, right? So most of the brims X-rays that we create are not going to be very high energy X-ray photons. All right, so I'm really kind of getting ahead of myself, but why don't we get hit by a lot of like asteroids and things like that? They burn up as one, but why don't most of them even burn up to get close enough to for the Earth to burn up.
Don't they get like in the gravitational pull of other planets?
Bingo. Jupiter, the sun, most of them fall into one of those, right? Because it's got a bigger gravitational pull, greater gravitational pull. So little bitty Earth, with all these electrons coming towards it, the electrons, in order to get in, or let's say the asteroids, in order to get into the gravitational pull of the Earth, have to get closer to the Earth. So the electrons, to be that greatly affected by the gravitational pull of the nucleus, likewise have to get close to the nucleus. So if our nucleus is tiny and we're sending these electrons towards it, the likelihood of getting close to the nucleus of the atom to have that kind of reaction, just a numbers game, probably not very good, right? So even though we get 1% of the X-rays created, and only 85% of those are brims, most of the brims, probably on an order of 1% of the brims, are worth anything. Now, what's the other way that we're going to create X-rays?
The characteristic.
Characteristic. And what does characteristic require? How does that happen? We get ejection of an inner shell electron, or we get ejection of an electron, right? So scrunching all this together, we got nucleus, we got electrons, we strike an electron, orbital electron with a projectile electron, knock it out, and if an electron drops into its place, we get a photon created, right? And that's characteristic X-rays. Now, where was our electron? Way over there, right? So what's the likelihood, if it's hard to get close to the nucleus of the atom and it's stationary, how much more difficult would it be to get to that one electron that's way over there that's not stationary? How likely would it be to hit that electron? You ever tried to throw a ball at, I don't know, your little brother and hit him in the head while he's running? Is it harder than whenever he's sitting still? Yeah, okay. So if this was tough, what do you think the chances of this happening are? Almost none. Exactly. So only 1% of the brims are going to be worth anything, maybe less than that. The likelihood of that happening is almost non-existent. So even in that 1% of the X-rays of what we create in the X-ray tube being X-rays, almost all of those are totally useless as well. Okay, and here's why. Is because of the atomic structure. So we've got the nucleus containing almost all of the mass. Okay, so if you flip over to page 30, bottom of the page you see table 2-1. So we're going to focus on 3 subatomic particles. We've got the electron, the proton, and the neutron. The different things you need to know about those 3 subatomic particles are the AMU describes, that's the atomic mass unit, describes the actual mass of the subatomic particle. The atomic mass number, which is right next to that, just says number, describes the rounded off equivalent to. So the charge is pretty obvious, the symbol is pretty obvious as well. So atomic mass unit, atomic mass number, and the charge. So what do you see in the electron compared to the proton? If we're looking at an atomic mass unit. Is it bigger, smaller? Smaller. A little bit smaller, a whole lot smaller. It's a whole lot smaller, right? So in comparison, what you've got in an atomic mass unit for the electron is you've got, in the proton you've got over 1. Okay, so it rounds off to a 1 in the atomic mass number. But the atomic mass unit is over 1, and if you look at the atomic mass unit of the electron, it's 0.0005. as effectively 0.00055. So what would that be? 55 100,000ths of a mass unit, right? So it's very small, it's extremely small. So what we're looking at is if your proton is yay big, then your electron is that big, right? So your proton is huge. Now look at the atomic mass unit of a neutron. What do you notice about it?
Slightly bigger.
Slightly bigger than the proton, right? So it's even bigger than the proton, and relative to the electron, it is even bigger, right? So most of the mass, the actual mass of the atom is located where? Almost all of the mass is going to be located inside of the nucleus. So now we've got a nucleus, or the nucleus of the atom. Let's say we represent the nucleus atom as maybe the size of an orange. So now our first set of electrons is going to be maybe as far away as the loop, right? So it's going to be a long, long ways away. Now apply what we were just talking about a second ago. If the gravitational pull of this nucleus is what is responsible for the loss of energy, the electron coming through the atom, then what it's going to have to do is get close to the nucleus of the atom, close enough to the nucleus of the atom to lose a significant amount of the energy to create an X-ray photon. And if we're talking about the area of an atom, the area of an atom is mainly empty space, just like the solar system, right? Solar system's almost always, or almost all empty space. Again, with these electrons, we're firing electrons at it, and the electrons are tiny, right? So the chance of sending an electron that is so small that we don't even recognize the mass of it, and it getting close enough to the nucleus of the atom to lose that much energy to create an X-ray photon of any energy level, any remaining energy level at all, is pretty slim, right? We're shooting something so small that we say it doesn't even really exist at something so small we can't see it. Chances of getting close to it, not good. So that's brims. But in characteristic, what we're doing is we're shooting something so small it almost doesn't exist at something so small it almost doesn't exist, right? So the chances of having that interaction, again, are very slim. Okay? So most of the mass, the actual mass, and it's important to differentiate between these two things. Most of the mass of the atom is located where? In the nucleus. What is found inside the nucleus?
Protons and neutrons.
Protons and neutrons, right? Most of the area of the atom is empty space, right? Mass, nucleus, area would be empty space. Okay? So, what we're going to have in most of our atoms is balance. We're going to have a set number of protons. So every atom, every individual atom of hydrogen is going to have how many protons? One. Every atom of helium is always going to have two. So what is it that the proton tells us? In an atom, what defines what the atom is? So we have hydrogen with one proton. We have helium with two protons. What if we take one of those away? What do we have? We have hydrogen. Right. So what defines what the atom is? The protons, number of protons. Okay? So that is our atomic number. Atomic number defines what the atom is, and it is what or how many positive charges are inside the nucleus of the atom. So if we have helium, we are always going to have two. anytime you have an atom that has two protons, only two protons in the nucleus, you're gonna have helium. Anytime you've got an atom that only has one proton in the nucleus, it's always gonna be hydrogen. Okay, so the number of protons gives us our atomic number. Our atomic number describes what the atom is. All right, so what we want is balance. So we've got protons, we've got neutrons, and what we'll talk about next week is that we can have almost any number of neutrons, theoretically, but if we have too many neutrons, then it becomes radioactive. And radioactivity is really just instability. The atom's too heavy for its atom type, okay? So if we have too many, we can theoretically have as many neutrons as we want, but if we get too many, then it's gonna try to get rid of those, and we'll talk about how it undergoes that later on. So we want balance. We've got protons, so what kind of charge do we have? What do we have if we have one proton and one neutron? You got what? It's not neutral. We got a proton, we got a positive charge, we got a neutral charge. Huh?
Positive.
It's positive charge, right. So it's positive charge, and we call that a charged particle is called a ion, right. So it's positive charge, it's an ion, so it doesn't want to be a positive charge, it wants to be a neutral charge, so it's gonna have attached to it an electron, okay? So your atomic structure, you're gonna have protons. Protons describe what the atom is, right? That is your atomic number. So number of protons describes exactly what the atom is. Number of neutrons vary a little bit, we'll talk more about that. But anytime we have one proton, we want to have one neutron. So in a helium atom, we've got how many protons? Two. So how many electrons are we going to have? Two. Right. If we don't have two, if we only have one, then what do we have? We've got a positive charge, which makes it a ion. Right. So if it has three, then what are we going to have? A negative charge, which makes it a ion. Right. Okay. So what, again, we want is balance. We want to have the same number of protons as we have electrons, and then we want to have a reasonable number of neutrons so that the elemental mass isn't so great that we have radioactivity. If we have radioactivity, then we're going to have, radioactive decay until it becomes neutral. We'll talk about that again next week. Okay? So, any questions on that? Why don't we pull it up there, because that's about as far as I got this morning before class. What we'll pick up with next week is electron arrangement, because the electrons are going to live in these orbits and specific energy levels and states. And we're going to look at how to calculate exactly how many each shell can have, and we're going to talk about the outer shell and how many it's going to have, and how we get different combinations of atoms to create different things and different ways we put them together. Okay? So any questions? Okay? So this is not Friday material, right? We're not testing on this on Friday. We're testing on chapter 1 on Friday. And again, just be here about 9:30, and we'll find a room, hopefully find a couple of rooms, one or two rooms, and all test together.
It's a multiple choice test, right?
Yes.
Okay, so bring a Scantron.
Bring a Scantron. 882, just a 100 question Scantron.